Hello, I am glad you're here with me continuing this journey on apportionment. Today's a little exciting because we're going to end talking about the apportionment method that the U.S. uses for its House of Representatives. But before we get there, I need to introduce what divisor methods are and show you a couple that have been used in our history before having that lovely ending with what's happening in our real world right now in the U.S. All right, so some methods of apportionment are divisor methods rather than quota methods. You end up using a divisor other than the standard divisor. Now, you can try the standard divisor first, and if it works, you can stop there and use it. But typically, you're going to need to make some adjustments based on what happens after you try the standard divisor. And so we call that a modified divisor. And so you modify the divisor, try it. If it works, great. If not, modify it again a little bit and keep trying it until it works. Then each of these three methods I have listed here, like Jefferson's, Webster's, and Adams's, all differ based on how we're going to do our rounding. Once we've found our modified divisor and done the division, like how are we going to go, like, are we going to round down, round up, use normal rules of rounding? What are we going to do? So that's where it really matters. And how do we make the decision what to do? Okay, so the first one, Jefferson's method, you determine a modified divisor to use in computing. They'll call it the modified quotas. Instead of standard quotas, since it's not the standard divisor, you're going to call it the modified quotas. In Jefferson's method, you want to choose it so that the total of the integers, after you've rounded each down to the nearest integer, that total is the number of items that's been apportioned. So you're basically determining what's called modified lower quotas, rather than just lower quotas in the quota methods. These are modified lower quotas. And then once you get the numbers to work, you apportion each group that quota. All right, let's use some data that we already have seen before from previous excursions talking about the quota methods. We have a situation where this country has these 5 states with specific populations. We have 1,320,000 in the first country. We have 1,515,000 in the second country. We have 4,935,000 in the third country. We have 1,118,000 in the fourth. And we have 1,112,000 in the fifth. Okay, so in this country, there was a standard divisor of 50,000. And they had, let's see, how many seats was it? There's 200 seats in the legislature. And when we worked with this before, we took those populations and divided by the standard divisor to find the standard quotas. And the standard quotas ended up being 26, you go back and compute these yourself, like do the divisions, 1,320,000 divided by 50,000 and so forth. But you get 26.4, you get 30.3, you get 98.7, we get 22.36, and you get 22.24. Now, since we are talking about Jefferson's method, what Jefferson said was you should be able to look at lower quotas and have those add up. Okay, so in this scenario, the lower quotas would be 26, 30, 98, 22, and 22. But when you add those up, what do you get? That's the key. 14, 16, 18, 3, 5, 14, 17, 19. Okay, so you come up too short. If we were doing a different method of apportionment, we'd have to figure out, how to hand out extras or whatnot, like Hamilton's method. But that's not what we're doing here. In Jefferson's method, he wanted all of those numbers to go ahead and add up to the 200 seats. So since they don't, now we introduce the whole modified quota concept. All right, so we're going to come up with a new quota. or a new divisor, and then come up with modified quotas and do the modified lower quota and figure out what comes out of that. I'm looking at this and I'm coming up short. Coming up with 198 when I need 200. So in division, if I need my answer to be higher, I make my divisor lower. You might be going, what? What are you talking about? All right, let's say I have a number like 40. If I divide 40 by 2, 40 is considered the dividend. 2 is considered the divisor. And the answer, 20, is the quotient. If I want the quotient to be bigger, then I need a smaller divisor. So in this case, I can only go down like to 1. Like let's say my divisor is 1. Well, then I would get a bigger quotient of 40. If I want a smaller quotient, then I need a bigger divisor. So let's say I take 40 and instead of dividing by 2, I divide by 5. Well, 5 goes into 40 8 times. So notice that my divisor went up from 2 to 5. Quotient went down from 20 to 8. I could take 40 and divide by 10, make my divisor even bigger, and my quotient goes down even more, down to 4. So it's kind of an opposite reaction here. And that's the kind of thinking I need to think about when I start trying to modify my divisors. Back up here, again, standard divisor of 50,000 wasn't right for getting the 200 seats. I came out short. So since I need the number to come up higher, then I need my divisor to be the opposite and be lower. So let's try a number like 49,350, which is lower than 50,000. Our sum will go up. Now this is where it's kind of a trial and error thing. We know we need to go lower, but we don't exactly know how much lower. I'll let you know a secret. I only know this because I'm taking this out of a book. But you try one, and if it doesn't work, then you're going to have to adjust and try again. So in these problems, they can be a little frustrating because you're not going to come up with the correct answer right away every time. It is a little guessing and checking. But after a while, you'll kind of get a feel for like roughly how much you want to adjust by how much you need it to change by. It gets better. Okay, so let's rewrite our states and their populations. So we've got the 1,320,000 for state A. We have 1,515,000 for state B. We have 4,935,000 for state C. We have 1,118,000 for state D. And we have 1,112,000 for state E. Okay, so we're using a different divisor here. So we're going to get modified quotas. So we're going to take 1,320,000 and we're divide by 49350. And we get what? 26.75. Okay. And since we're using Jefferson's method, we want the modified lower quota So we just take that modified quota we just got and we go down to 26. We drop off the decimal part. That's basically what we're doing. Okay, so 1,515,000 divided by 49,350. That gives us 30.70. We'll just round it to 2 decimal places for now. That's sufficient. Which means the modified lower quota will be 30. We'll take 4,935,000 divided by 49,350. And we get a nice even 100. Very nice. So that ends up just being 100. Okay. 1,118,000 divided by 49,350. We get 22.65. That ends up being 22. And then 1,112,000 divided by 49,350. We get 22.53. That ends up being 22. All right, so what do those add up to? Let's use a little different color here. Let's add those up. 8, 10, 3, 5, 8, 10, 200. Those add up to 200. Let me double check in my trusty calculator here. 200, yep, they do. There we go. So it worked. So there's your apportionment. State A would get 26, State B would get 30, State C would get 100, States D and E would both get 22. And that's by Jefferson's method. If it hadn't worked, like let's say I came in too low and I needed to go higher, then I would have to lower my divisor further. If I came in too high, then I need to go lower, then I'd have to raise my divisor. The direction I need to go, I do the opposite to my divisor. Okay, so this method was created by Thomas Jefferson. I'm sure you've heard of him a few times now. Third president of the United States. He had his hands in a lot of things, including the Declaration of Independence, the Louisiana Purchase, and mathematics. Louisiana Purchase, just a little side note, if you're not real familiar with history, it's actually something very interesting to learn about. It's the reason that we're able to be such a large continent, continental 48 states and everything. It was the beginnings of really expanding. But anyways, so this apportionment method eliminated the need to divide up leftovers that existed when we were looking at Hamilton's method and Lowndes' method and things. So he was able to get President Washington to veto that congressional decision to use Hamilton's method. So that's how he convinced Washington that it would work better. It's like, oh, we don't even have to worry about the leftovers if we just keep modifying the divisor and force it to work. Okay, next one, Webster's method. So Webster's method isn't drastically different. You're using a modified divisor, but you want to use the normal rules of rounding, round to the nearest integer, and that should be your number of items apportioned. So you're going to do a modified rounded quotas and then apportion the group what you get. All right, so back to our data with states A, B, C, D, and E. Oop, I like black better for this. Sorry, okay. Now, from what we had earlier, once again, we had, I'm not going to write all the populations again. By our standard quotas, we had what, 26.4, 30.3, 98.7, 22.36, and 22.24. Well, by Jefferson's method, if we wanted to look at our rounded quota, 26.4 would round down to 26, 30.3 would round down to 30, 98.7 would round up to 99, 22.36 would round down to 22, and 22.24 would round down to 22. Remember, you're just looking at that first decimal place, and if it's 5 or higher, round up. If it's less than 5, just the integer part stays the same. So if we follow that, like Jefferson likes, or I'm sorry, not Jefferson, like Webster likes to do, then the total is too low. Need to go higher. So use a lower divisor. So remember, 50,000 had been the original divisor when we were just doing standard divisor, standard quota, etc. For this example, for Webster, let's try 49,700. And again, if it doesn't work, we'll have to adjust it further. If it does work, great, we're done. And you can have more than one divisor that works. You and then a classmate working next to you might have two different divisors. They might both work, and that happens. It's like a range of numbers that'll make it work. So don't despair that you're trying to find like that needle in a haystack with this, because there are more than one option in many cases. Okay, so back to our states. Okay, so if we took 1,320,000 and we divided by 49,700, we would get 26.56 as a modified quota. Okay, and according to Webster's method, we're going to go ahead and just round that to the nearest integer, so we're going to say 27. Okay, for state B with 1,515,000, we're going to divide that by the 49,700, 30.48, which would round to 30. State C, 4,935,000. Divide that by 49,700, 99.30. So rounds to 99. State D with 1,118,000. Divided by 49,700. We get 22.49. Which rounds to 22. I carried at least 2 decimal places. That'll make it more accurate for you. 1,112,000 is in the last one. Divide that by 49,700. 22.37. So that rounds to 22. Okay, so add them up. I'm getting 200. Let me double check in my trusty machine here. And I get 200. Perfect. That's what I wanted. I wanted 200. Yay! So that works out. So this was devised by Daniel Webster, a lawyer, orator, and senator. Hamilton's and Jefferson's methods both favor larger states. So it gets pretty political here. This is a little bit of a compromise. Not biased in favor of larger states. All right, one more method before we get to that grand finale. Adams's method. Determine a modified divisor to use in computing the modified quota. This divisor is chosen so that the total of the integers with each rounded up to the nearest integer is the number of items apportioned. So you're determining modified upper quotas. And then you apportion each group its quota. All right. so back to our data earlier. Same data, states A, B, C, D, and E. Remember, with the standard quota, we had 26.4, we had 30.3, we had 98.7, 22.36, and 22.24. So, according to this method, we're doing the whole modified upper quotas. So we'd have, what, 27, 31, 99, 23, 23. What does that add up to? That's looking like it's too big. Let me double check on my trusty calculator, but just in case. Yeah, 203. Too big. I need to go down. I need my total to go down from 203 to 200. So if I need to go down in my total, I'm going to need my divisor to go up. So remember the divisor before was 50,000. Let's go ahead and try 50,600 and see what that does for us. Again, if it doesn't work, then we'll have to adjust the divisor and try it again until we find one that works. You have to kind of look at it, see if you went too high or too low, and adjust accordingly. All right, so you have your state's populations, and we're going to be looking at the modified quota and then modified upper quota. So if we do 1,320,000, it's so easy to accidentally mistype and not put enough zeros in, so be careful. I almost did that just now and I caught myself. I get 26.09, which will bump up to 27. All right, for 1,515,000, do that. Divide by 50,600. I get 29.94, which bumps up to 30. 4,935,000. Divided by 50,600. 97.53. Bumps up to 98. 1,118,000. Divided by 50,600. 22.09. Bumps up to 23. 1,112,000. Divided by 50,600. 21.98. Bumps up to 22. All right, let's add them up. It's looking promising, but let me double check by adding in my calculator. And it worked. Woohoo! If it hadn't worked, like let's say my number came out too high, like let's say it came out to 201, that means I need to go lower, which means my divisor would have to go higher. If it came out too low, like let's say it came out to 199, I would need to go higher, so I would try a divisor that was lower. And just keep adjusting until it works. So that's what you got to do. Nice, huh? So John Quincy Adams presented this method in 1832, which favors smaller states. The method was never actually put into use. So it exists, but never actually made it into our history books. All right, the Huntington Hill method. This is the exciting one. This method was developed when Edward Huntington, a Harvard University professor, built on a scheme developed by Joseph Hill, a statistician for the U.S. Census Bureau. In 1941, Congress officially adopted it for apportioning seats for the U.S. House of Representatives. It rounds the modified quota based on whether the modified quota is less than or greater than the geometric mean of the whole numbers directly before and after it. And Congress still uses it today. We are not going to take state data right now and to try to apply it. We're just going to use some existing data from a book that I have called A Mathematical View of Our World. And we're going to see exactly how that works. Okay, so let's say we know we have states. Let me do this. I don't like writing in black. Okay, so we have states A, B, C, and D. And these states had modified quotas of 10.47, 3.47, 5.47, and 7.59. Okay, then we need to decide to round using the Huntington Hill method. That's the requirement. So the first thing we need to do is find out, what is a geometric mean? What the heck is that? The geometric mean of two numbers, A and B, is the square root of A times B. So when we're looking at our states, we have our states, we have their modified quotas. We're going to be looking at those modified quotas and finding the geometric means. So like for a modified quota of 10.47, what we do is we take the integer part of 10 and we take the next integer up, 11, and we do the square root of 10 times 11. And you put that in your calculator. And you get around 10.488. Now, since the modified quota, I'll just put Huntington Hill method here. Now, since the modified quota is 10.47, which is less than the geometric mean, then we're going to round down to 10. We're going to use that modified lower quota. Okay, state B had a modified quota of 3.47. Geometric mean, you're going to do square root of the 3 times the next one up, 4. So square root of 12. And you get around 3.464. Well, your modified quota of 3.47 is higher than the geometric mean of 3.464. So that means we're going to bump it up from 3.47 to 4. 5.47 for state C. Geometric mean is the square root of the 5 times the next one up, 6. So square root of 30. And we get 5.477. Now the 5.47 is less than the geometric mean of 5.477, so we're going to stay at 5. And then finally state D, 7.59. Geometric mean is square root of the 7 times the 8, so square root of 56. So we get 7.483. Now since the 7.59 is higher than the 7.483, we're going to go up to 8. And that's how it's done. So like you go through all the states, and you do you have each, like all the states in the U.S. and all the things that get representation, and you come up with these modified quotas based on how many people there are, based on how many seats each state gets, etc. And then to decide how to round, you use the geometric mean. If that modified quota of each state is less than the geometric mean, then you just stick with the integer part. If that modified quota is bigger than that geometric mean, then you bump up to the next integer. And there it is. And that's how they decide how to apportion all the representatives in the US. That's their little rule. So that's the Huntington Hill method. So there you go. I mean, hopefully that was as exciting as I've made it out to be. All right, I hope you enjoyed that. This wraps up the different apportionment methods that we're going to cover in this class. So next we're going to need to talk about flaws in apportionment, just like we talked about flaws in voting. We're going to do that here too with apportionment. So just look forward to that video appearing pretty soon. Thank you.